What were the first prehistoric land animals capable of murder? Full prehistoric documentary. Beneath the shadowed canopy of the Devonian floodplains, the first land animals prowl with silent intent, bodies coiled for sudden violence. Over 370 million years ago, the stage of Earth shifted from water to soil as pioneering vertebrates tested legs, jaws, and cunning against a world unprepared for their ambition. Predation emerges not as an accident but as a design, shaping ecosystems, forcing innovation, and redefining survival itself. Every footprint and gnash hints at the dawn of lethal strategy, where intellect and instinct intertwine. Step into the hunt, tracing the earliest killers and uncovering how life first mastered murder on solid ground. The first hunter, on unsteady legs, Watcheria. Moist air drifted across the braided channels of the late Mississippian floodplains, where stands of horsetails and early lycopsids formed tangled green corridors along the water's edge. And it was within this shifting zone of mud, silt, and shallow pools that Watcheria deltae began testing the promise of land, driven by anatomical innovations that marked one of the earliest experiments in terrestrial predation. Its fossils, recovered from the delta localities of Iowa and dated to roughly 340 million years ago, reveal a creature that already departed from the purely aquatic habits of its Devonian predecessors, displaying limb bones with strengthened joint surfaces capable of supporting partial body weight on firm substrates rather than relying solely on buoyancy. Layers of shale and micaceous sandstone preserving Watcheria's remains contain ripple marks and plant impressions that reconstruct a low-gradient river system prone to fluctuating water levels, and such conditions would have favoured the rise of predators able to exploit stranded prey during seasonal retreats of the shoreline. The humeri and femora of Watcheria possess expanded muscle attachment sites that paleobiologists interpret as signs of improved propulsion during shallow water lunges, suggesting that the animal could surge forward with substantial force even when its body was only partly submerged. These features differentiate it from earlier stem tetrapods like Ichthyostega, whose limbs were still optimized for aquatic propulsion rather than weight-bearing excursions onto sediment bars. Cranial analyses of Watcheria show a tall, narrow skull armed with marginal teeth, shaped for gripping slippery prey such as early actinopterygians and soft-bodied invertebrates, but the presence of recurved fangs on the premaxilla hints at the ability to puncture tougher integument once it approached unfortunate vertebrates drawn into the shallows. Computed tomography of the skull has revealed robust palatal dentition arranged in arcs that could anchor fleeing prey, allowing the predator to twist its head and tear free sections of flesh, a behaviour inferred through comparative biomechanics with later Carboniferous anthracosaurs. Such a feeding apparatus implies a powerful bite cycle, made even more efficient by the strengthened quadrate articular joint found in several well-preserved skull fragments. One of the most revealing insights into Watcheria's predatory potential comes from the microanatomy of its limb bones, whose cortical thickness suggests a physiology capable of brief terrestrial excursions without risking structural collapse, meaning that the animal was not restricted to ambushing in water alone, but could haul itself onto firm land to pursue temporarily beached prey. Cross-sectional thin sections display growth zones consistent with a relatively fast ontogenetic trajectory compared to Devonian forms, possibly indicating a more active lifestyle supported by improved oxygen uptake through both lungs and cutaneous surfaces. These shifts in skeletal architecture mark a turning point in vertebrate evolution, the moment when early tetrapods became not merely water-edge opportunists, but intentional hunters navigating two domains. Sedimentological studies surrounding Watcheria fossil beds indicate periodic flooding events capable of redistributing fish carcasses, amphibian bodies, and invertebrate clusters into ephemeral pools, creating hotspots of decomposing organic matter that would have attracted small scavengers and provided predictable hunting grounds for larger predators. Taphonomic patterns reveal that Watcheria likely patrolled these nutrient-rich pockets, striking at organisms trapped in shrinking water bodies during dry intervals. A strategy echoed in modern amphibious predators like mudskippers or crocodilians during drought cycles. The distribution of tooth-marked scale fragments suggests that Watcheria did not always rely on stealth alone, but may have engaged in rapid strikes, supported by limb-propelled lunges. The vertebral column of Watcheria shows intercentra and pleurocentra arrangements, consistent with early experimentation in load distribution on land, and although its ribs were not sufficiently robust to prevent lateral body sagging, they did provide enough structural support to stabilize slow terrestrial movements. This mosaic physiology, neither fully aquatic nor confidently terrestrial, created an evolutionary bridge, allowing predatory behavior to expand into new ecological zones. Paleontologists have noted that the animal's likely gait, informed by comparisons with trackways of similar-bodied taxa, would have been a semi-sprawling shuffle, allowing Watcheria to approach the margins of tidal channels and strike at organisms unaware that a vertebrate hunter could emerge from the water with such speed. The reconstructed musculature of the skull and pectoral girdle suggests that Watcheria possessed rapid head-lifting ability, enabling it to thrust its jaws upward toward prey at the water's surface or to snap downward onto creatures crossing muddy banks. This movement, combined with the serration pattern found along some replacement teeth, points toward a predatory repertoire capable of both seizing and processing meat, revealing the earliest evidence for a dual-function attack adapted to life beyond a purely aquatic realm. Such adaptations imply heightened ecological pressure, favoring predators that could exploit both aquatic prey and the vulnerable creatures transitioning onto land. Isotopic analyses of fossilized bone phosphate from associated fauna reveal fluctuating salinity gradients in the region, indicating that Watcheria inhabited environments subject to varying water conditions, which would have required behavioral flexibility in pursuit strategies. During wetter phases, it may have hunted amid dense vegetation along river margins, whereas in drier cycles, it could take advantage of stranded vertebrates forced into dwindling pools. The ability to shift between prey sources in a rapidly changing Devonian Mississippian ecosystem speaks to its resilience as a predator whose survival hinged on exploiting ecological instability. Further clues arise from the inner ear morphology preserved in partial brain cases, which suggests improved balance and spatial awareness relative to earlier tetrapodomorph fishes, a trait critical for coordinating movements in shallow water and on uneven land surfaces. This refinement of sensory systems would have allowed Watcheria to track prey movements through subtle substrate vibrations, granting it a significant advantage in murky environments where visibility was limited. Combined with enhancements in jaw leverage and limb stabilization, these sensory developments illuminate an animal prepared to extend its predatory reach into environments no previous vertebrate had mastered. The surrounding flora of its habitat, dominated by towering club mosses and early seed ferns, created a complex network of roots, fallen stems, and silted clearings where small arthropods, mollusks, and juvenile tetrapods sought refuge, inadvertently forming an intricate lattice of hunting opportunities for Watcheria. Palynological analysis of spore assemblages shows high humidity and dense vegetation, conditions that fostered both prey abundance and cover for ambush strategies. By maneuvering through submerged plant tangles and over partially exposed roots, Watcheria refined an emerging form of terrestrial stealth, setting the stage for later vertebrates to become fully land-based predators. Understanding Watcheria is to witness the dawn of terrestrial murder, a moment when vertebrate life first recognized that land could be more than a barrier. It could be a battlefield ripe with opportunity for those bold enough to crawl onto its uncertain surface. Its blend of aquatic power and embryonic terrestrial capability created a prototype for millions of years of hunters to come, and its hesitant forays onto mud and root-tangled shores began a lineage that would eventually lead to predators that no longer relied on water to strike. As its unsteady limbs pressed into the yielding soils of ancient floodplains, they carved the first outlines of a future where more confident stalkers would push deeper into the forests of the Carboniferous, refining the predatory legacy Watcheria had only begun to imagine. The low-slung shadow, Greer epiton. In the dim stillness that follows Watcheria's early experiments on land, the Carboniferous world reveals a hunter shaped by secrecy rather than courage, a creature whose entire existence unfolds where water, fog, and decaying vegetation blur into one continuous realm of concealment. Here, in an ecosystem dominated by towering lycopsids and spiraling calamites, Greer epiton extended the evolutionary story in a direction defined not by bold steps onto land, but by patient attention to every quiver moving through the swamp. Fossils of this early amphibian place it in the Mississippian portion of the Carboniferous, around 335 million years ago, when the forests were new, vast, and suffocatingly humid, creating environments where predators could thrive by remaining unseen for hours before a single decisive strike. Along the margins of sluggish blackwater channels, Greer epiton extended its elongated body through mats of club moss roots and decaying fronds that lay half submerged beneath a canopy dense enough to limit direct sunlight to flecks that drifted like dust motes. This arrangement of vegetation created natural blinds, and its body, long, low, and serpentine, fit these spaces with uncanny precision. Measuring around a meter in length, it relied on a mix of lateral undulation and subtle paddling motions to maintain near-silent movement, a strategy made possible by its high vertebral count and flexible axial skeleton. These anatomical traits suggest a predator that preferred the transitional boundary between land and water, where prey frequently paused, unaware that a patient killer lurked centimeters away. With a skull flattened into a hydrodynamic wedge, this creature turned its very profile into a weapon designed for surprise, allowing it to slip forward beneath floating plant debris until only its nostrils and eyes breached the surface. The skull of Greer epiton, broad, low, and heavily ornamented, reveals sensory grooves that likely supported a lateral line system, enabling it to detect subtle vibrations transmitted through waterlogged substrates. This sensory advantage is a hallmark of early tetrapods that remained tied to aquatic hunting strategies even as their limbs grew more defined. The premaxillary and maxillary bones bore small but recurved teeth, suited for gripping rather than tearing, indicating a reliance on rapid capture followed by whole prey ingestion, a behavior consistent with suction-feeding origins. Through the dense soup of humid air, sensory systems honed by millions of years of aquatic ancestry detected faint disturbances that betrayed unwary prey, especially juvenile amphibians and small arthropods traversing the wet leaf litter. Carboniferous ecosystems boasted an extraordinary diversity of arthropods, from early millipedes, such as Arthropleura juveniles, to primitive insects that had not yet evolved flight, and each movement across waterlogged soil produced vibrations exploited by Greerappeton's canal systems, its sensory acuity extended beyond simple detection. Fossil analysis suggests that variations in canal diameter reflect differing sensitivities to pressure changes, meaning this animal likely interpreted not just movement, but the size and direction of moving organisms in its vicinity. Inside the shaded labyrinth of a carboniferous swamp, limb joints built for subtle pushes rather than confident strides enabled brief but deadly excursions onto firmer ground when prey lingered near the shoreline. The limbs of Greerappeton were relatively small compared to its body, with robust proximal bones but reduced distal elements, forming an arrangement capable of shuffling rather than walking. Their orientation indicates a sprawling posture, which limited stride length but allowed low-slung stability in shallow water. This posture functioned well for anchoring during sudden lunges, and the articulations of the humerus and femur suggest joint flexibility optimized for adjusting attack angles rather than supporting prolonged terrestrial locomotion. When paleontologists uncovered Greerappeton fossils within the East Kirkton limestone, they found evidence of a predator whose anatomy echoed its environment's oppressive mood, preserved alongside rocks that formed in ancient lakes, periodically fed by volcanic hot springs. These surrounding sediments reveal cyclic depositional patterns, with lamination indicating still water environments punctuated by episodes of disturbance, possibly from storm runoff or volcanic activity. This geological context helps constrain the habitat conditions Greerappeton inhabited. Warm, mineral-rich waters that supported dense microbial mats and a variety of invertebrates. Associated fossil fauna, including early temnospondyls, primitive reptiles, and fish, paints a picture of a complex food web within which Greerappeton held a mid-level predatory role. Every preserved vertebra, rib, and skull fragment testifies to a lifestyle in which ambush, not pursuit, defined the art of killing, reinforcing the notion that its success depended on controlling the moment of first contact. The vertebrae possess pronounced neural spines, which likely supported strong axial musculature used in sudden forward thrusts through water. While many early tetrapods experimented with ways to use their limbs to increase mobility, Greerappeton doubled down on axial propulsion as its primary locomotor strategy. This specialization suggests that whenever prey approached, the predator relied on an explosive surge rather than protracted movement, a tactic that conserved energy while maximizing lethal efficiency. Within these same fossil beds, sediment textures and associated flora reveal the character of the swamp that trained this animal into a patient murderer, where oxygen-poor waters slowed decay and preserved remains long enough for scavengers to frequent the channels. Such waters also limited the escape options of prey animals, making the boundary between aquatic and terrestrial surfaces especially dangerous. Lycopsid roots formed intricate tangles that created natural pitfalls, forcing smaller vertebrates and arthropods to navigate narrow openings where Greerappeton could lie in wait. These structural complexities, captured in the sedimentary record, demonstrate how ecosystem architecture shaped predation strategies in early terrestrial environments. Among the layered impressions of lycopsid bark and ancient silt, clues to Greerappeton's feeding mechanics suggest rapid suction and sudden forward lunges, movements that depended on cranial kinesis and rapid expansion of the buccal cavity to generate pressure differentials. Although true kinesis is debated, the robust connection points for jaw muscles indicate a powerful snap rather than a prolonged bite, matching patterns seen in aquatic strike feeders. The arrangement of the hyoid apparatus supports the idea that it could create suction currents, allowing it to pull prey toward its teeth before they could retreat. This combination of tactics reflects a predator that maintained ancestral feeding strategies while adopting new spatial opportunities at the land's edge. As the Carboniferous forests thickened and the waterlogged ground grew increasingly labyrinthine, predators like Greeropeton learned to weaponize concealment itself, turning every shadowed pool into the mouth of an unseen trap. High atmospheric oxygen levels fueled dense plant growth, making underbrush and surface debris more extensive than anything previously seen in Earth's history. This abundance transformed the physical environment into a three-dimensional maze, where vertical plant structures, lateral root networks, and floating mats all provided layers of cover that favored ambush specialists. In this context, Greeropeton's elongated body and reduced limbs were not hindrances, but evolutionary advantages. From this quiet dominion, the lineage that followed began drifting closer toward independence from water, hinting at hunters whose limbs would soon stiffen into tools of terrestrial certainty, leaving behind the low-slung shadows of the swamp for the assertive stride of predators wholly committed to land. Greeropeton's world, built upon ambiguity and half-submerged silence, could only hold dominance temporarily because evolution was preparing creatures capable of moving with confidence where it could only creep, and as its era of shadow-bound ambush receded into geological memory, the next generation of killers emerged with claws, spines, and skeletal reinforcements suited for a new kind of predation that no longer depended on the water's quiet embrace. The first true land stalker, Hylonomus. Beyond the retreating reach of stagnant waters, the forest floor reveals a new kind of killer, shaped not by patience, but by precision. No longer constrained by the need for aquatic ambush, Hylonomus moved with a compact agility that allowed it to traverse dry leaf litter, fractured soil, and root-laden clearings with subtlety and speed. Measuring roughly 20-30 centimeters in length, it occupied an evolutionary niche, entirely different from its amphibious predecessors. A predator confident in fully terrestrial environments, preying on insects, juvenile tetrapods, and rival micropredators that shared the forest floor. Fossil evidence from the Joggins Formation in Nova Scotia, dating to approximately 315 million years ago, places it among the earliest reptiles whose anatomy signaled complete independence from water for hunting and reproduction. Under the shifting mosaic of light filtered through primitive conifers, a compact reptile threads its body with deliberate poise, weaving through the shadows cast by towering lycopsids and ferns. Its limbs, although small, were positioned beneath the body more effectively than Greeropeton's sprawling configuration, providing a spring-loaded posture for quick lunges and agile maneuvers. Osteological analysis shows reinforced humeri and femora with pronounced muscle attachment sites, reflecting the development of rapid terrestrial locomotion. Unlike its semi-aquatic ancestors, Hylonomus could sprint along uneven surfaces, climb over decomposing plant matter, and maintain balance across irregular terrain, transforming the forest floor into a three-dimensional hunting arena. Beneath scattered layers of brittle leaf litter, traces of early arthropod life provide both opportunity and competition. From primitive cockroaches and silverfish to small myriapods, coprolites found in associated deposits suggest that Hylonomus actively consumed a mixture of invertebrates and small vertebrates, marking it as one of the first reptiles to exploit a fully terrestrial food chain. Its teeth, small, sharp, and slightly recurved, were well suited for grasping and puncturing delicate exoskeletons or soft-bodied prey, demonstrating an evolutionary optimization for speed and precision rather than brute force. Such dentition, combined with its skeletal adaptations, allowed Hylonomus to dominate niches inaccessible to bulkier amphibious hunters. Perched atop ridges of dried root systems, Hylonomus displays a confidence impossible for its amphibious ancestors. Each careful step, a rehearsal for sudden, explosive lunges at prey. Limb joints articulate with ga-reta range of motion than previously seen in early tetrapods, enabling lateral turns, rapid direction changes, and controlled leaps. Comparative studies of limb proportions indicate that it could generate significant acceleration relative to its body size, providing an early template for the small, cursorial predators that would later proliferate in terrestrial ecosystems. Its long tail acted as a counterbalance, stabilizing rapid movements and enhancing precision during complex maneuvers over uneven terrain. Around the branching network of early seed plants, the emergence of the amniotic egg becomes an evolutionary turning point, freeing Hylonomus from dependence on water for reproduction. Fossilized nests and plant-associated sedimentary traces suggest eggs were laid in moist, shaded microhabitats beneath fallen cones or decomposing ferns. This reproductive innovation not only allowed the species to colonize fully terrestrial habitats, but also reduced vulnerability to aquatic predators, giving small reptiles a selective advantage over amphibians like Grere epiton. By decoupling reproduction from aquatic environments, Hylonomus marked a decisive step toward the rise of modern reptiles and the eventual dominance of terrestrial vertebrate predators. Between the minute shadows cast by towering club moss trunks, skeletal adaptations signal a profound departure from water-bound strategies, including a reinforced vertebral column and ossified limb girdles capable of supporting repeated terrestrial strikes. Histological studies of limb bones show tightly packed growth lines indicative of rapid, sustained activity consistent with a lifestyle demanding quick reactions, repeated sprints, and frequent ambushes. Unlike its predecessors, Hylonomus relied on structural integrity in dry, uneven terrain, enabling extended activity periods in daylight or twilight without the buoyancy assistance previously provided by water. Through narrow corridors of rotting bark and fern stipes, Hylonomus encounters rivals equally eager to dominate this miniature battlefield. Paleoecological reconstructions suggest it competed with other early amniotes, small temnospondyls, and predatory arthropods for food, requiring both strategy and speed. Fossil associations indicate overlapping territories and potential interspecific interactions, where successful predation depended not solely on anatomy, but also on spatial awareness and exploitation of microhabitats. The subtle interplay of predator and competitor illustrates the complexity of early terrestrial ecosystems and the selective pressures that refined Hylonomus's predatory toolkit. Against the subtle crackle of drying vegetation, the reptile's feeding mechanics illustrate a shift toward rapid, forward-facing strikes, combining lateral head flicks and precise jaw closure to immobilize prey instantly. Cranial anatomy indicates increased bite force relative to skull size and reinforced palatal structures to handle struggling insects or small vertebrates. Muscular reconstructions suggest a high degree of coordination between forelimbs and jaw, allowing it to pin prey while delivering a precise bite, a behavior impossible in sprawling, semi-aquatic amphibians. This efficiency demonstrates the evolutionary advantage of skeletal stiffening and limb realignment in enabling fully terrestrial predation. Within the fossil-rich deposits of the Joggins Formation, paleontologists find preserved evidence of a predator making full use of its new terrestrial freedoms, including trackways and occasional coprolites that reveal hunting strategies. Fossil impressions show stride lengths consistent with agile maneuvering rather than lumbering locomotion, while bone orientation in disarticulated skeletons suggests rapid escape responses to larger predators. These data provide insight into how Hylonomus navigated both physical challenges of the forest floor and ecological pressures from contemporaneous fauna, establishing itself as an early model of a true land-based hunter. Amid the stillness that settles over the forest after each successful hunt, ecological clues reveal a landscape in the early stages of vertebrate partitioning, where size, speed, and reproductive innovation define survival. Hylonomus exemplifies this process, carving out a niche distinct from semi-aquatic amphibians and avoiding direct competition with larger predators while mastering smaller prey. Its presence reflects the interplay of anatomy, behavior, and environment, highlighting the importance of micropredators in shaping the broader evolution of terrestrial ecosystems. Overground hardened by seasonal drying, selective pressures intensify, encouraging faster reflexes and more assertive foraging routes, producing early terrestrial specialists with greater independence from aquatic habitats. Each hunting success reinforced behavioral and morphological trends that would be echoed in the lineage of reptiles to come, foreshadowing increasingly agile, decisive predators. Hylonomus's small size belied its evolutionary significance. It was a harbinger of the land-dwelling carnivores that would dominate the forest floor for millions of years. Upon this fledgling terrestrial arena, the small reptile's evolutionary gamble foreshadows larger predators, whose footsteps will soon shake the same forest floor, heralding a future where claws, speed, and fully terrestrial locomotion redefine the meaning of predation. In embracing dry land with agility, precision, and reproductive independence, Hylonomus leaves behind swamp-bound ambiguity and opens a new era for vertebrate hunters. Its successes and innovations set the stage for the escalation of predatory diversity that will follow, a world where small but confident stalkers become the architects of a more brutal terrestrial food web. Blade-toothed, sovereign Dimetrodon grandis. Standing at the edge of a sun-baked Permian plain, the forest floor feels small beneath the shadow of a predator engineered for domination. Dimetrodon grandis, reaching lengths of up to 4 meters, casts an imposing presence over the open floodplains and seasonal woodlands of the early Permian. Its heavy, muscular body was designed not for stealth, but for power and authority, each step reverberating through hardened soil. Unlike the darting, cautious movements of Hylonomus, Dimetrodon relied on overwhelming force, crushing prey with jaws built to slice through bone and sinew alike. Fossils from Texas, Oklahoma, and parts of Europe reveal it as the archetype of apex terrestrial predation, an evolutionary leap in both size and lethal specialization. Rising under the imposing sail that towers like a living banner, every ridge of bone and sinew signals lethal precision. The neural spines, some exceeding 60 centimeters, supported a sail of skin and connective tissue that likely served multiple purposes: thermoregulation, display for territorial dominance, and possibly intimidation of rivals. This sail, combined with a heavily muscled body, communicated the physical and ecological authority of Dimetrodon across the Permian landscape. Its silhouette alone would have warned competitors and prey alike of the predator's unmatched potential to enforce its rule over the forest floor and riverine corridors. Stretching over the cracked, parched soil, massive claws press into the earth, evidence of a hunter built to overpower and control. The robust limbs, while not built for long-distance pursuit, allowed short bursts of acceleration and exceptional stability during attacks. Fossilized tracks indicate a sprawling gait slightly modified for terrestrial agility, enabling it to pin struggling prey while absorbing recoil forces from a crushing bite. Each claw, each tendon attachment, and each vertebral articulation reflects evolutionary engineering designed for domination, rather than evasion, a stark contrast to the cautious micropredators that preceded it. Within the elongated skull, serrated teeth curve with calculated intent, engineered to grip, slice, and fracture bone with each strike. Bite force reconstructions estimate pressures capable of shattering small amphibian bones, enabling Dimetrodon to feed on a variety of vertebrate prey. The combination of sharp incisors and laterally compressed blade-like teeth suggests a feeding strategy that was both opportunistic and efficient, minimizing struggle while maximizing caloric intake. Cranial sutures reveal a reinforced architecture capable of withstanding torsional stresses during prey capture, underscoring the predator's evolutionary investment in lethality. Scattered among sparse conifer clusters and early seed ferns, fossil footprints suggest territorial ranges measured in hundreds of meters, not the confined shadows of micropredators. Dimetrodon likely patrolled broad areas in search of vulnerable prey, asserting dominance over multiple ecological niches. The preservation of trackways near shallow waterways suggests that, unlike amphibious hunters, it could traverse both open plains and the edges of aquatic habitats with ease. Its presence influenced the distribution and behavior of contemporaneous reptiles, amphibians, and arthropods, establishing a hierarchy dictated not by cunning alone, but by sheer physical supremacy. The vertebral column and limb articulations reveal a balance between brute strength and surprisingly agile torsion, allowing both short bursts of speed and precise positioning over prey. The flexible spine permitted subtle adjustments during attacks, enabling Dimetrodon to twist and pivot while maintaining its enormous bite force. Limb morphology shows strong flexor and extensor muscles, facilitating powerful lunges and stabilizing movements during struggles with prey. These anatomical adaptations allowed it to act as both an ambush predator and an opportunistic hunter, combining static strength with dynamic action in a way few contemporaneous species could match. Heat-sensitive vascular channels within the sail hint at thermoregulatory mastery, offering insights into energy management for a predator whose metabolism could sustain prolonged dominance. The Permian climate, marked by extreme temperature fluctuations and seasonal droughts, demanded physiological innovation. By regulating body temperature through controlled blood flow in the sail, Dimetrodon could optimize digestion, activity, and energy allocation for hunting. This adaptation, coupled with its apex status, allowed it to maintain both physical dominance and ecological control over its habitat, outperforming competitors in endurance and metabolic efficiency. Paleontologists examining skull sutures and jaw musculature deduce bite forces capable of puncturing armored prey, reinforcing its role as the Permian apex. Comparisons with smaller sphenocodontids suggest a rapid escalation of predatory capability within the synapsid lineage. The combination of cranial reinforcement, muscle attachment sites, and dental specialization underscores the evolutionary pressure to exploit larger, tougher prey and dominate terrestrial ecosystems. Dimetrodon's anatomy was a statement of apex authority, a template for subsequent synapsid predators, and a milestone in the terrestrialization of hunting strategies. Embedded in sediment layers and fossil associations, evidence emerges of prey choice, ranging from amphibians to early reptiles, revealing a generalist strategy tempered by opportunistic specialization. Isotopic analysis of fossilized teeth and coprolites supports a varied diet, while site-specific fossil concentrations indicate predation near water edges where amphibians congregated. Such ecological versatility allowed Dimetrodon to stabilize its populations while influencing the behavior and evolution of prey species. Its generalist predation strategy illustrates the emergence of ecological hierarchies, where apex predators controlled both species abundance and habitat usage. In the wider context of Permian ecosystems, Dimetrodon's dominance shapes the behavior, distribution, and evolution of other terrestrial vertebrates, exerting a top-down ecological influence rarely seen before. Smaller reptiles and amphibians adopted nocturnal or evasive strategies to avoid encounters, while herbivores adjusted feeding patterns and habitats to minimize risk. Dimetrodon's presence catalyzed ecological partitioning and evolutionary experimentation in its contemporaries, reinforcing the principle that apex predators indirectly drive diversity and innovation in terrestrial ecosystems. Each anatomical detail, from spine to phalanges, reflects an evolutionary experiment perfected for terrestrial rule, a contrast to the cautious stalking of small reptiles like Hylonomus. From cranial design to limb configuration, every element was optimized for lethality and endurance. Unlike its predecessors, Dimetrodon ruled its environment with unchallenged authority, a predator whose very existence rewrote the ecological balance. Its dominance exemplifies the culmination of evolutionary trends that began with tentative land-hunting reptiles and continued through increasingly specialized synapsids. As the Permian sun sets on a world of temporary equilibrium, the apex predator's reign foreshadows both the eventual collapse of its ecosystems and the emergence of new, unpredictable killers. Dimetrodon's success, though absolute in its time, set the stage for ecological instability that would eventually reshape terrestrial life. The predator's architecture, behavior, and influence serve as both a pinnacle and a precursor, hinting at the evolutionary upheavals to come, where extinction, adaptation, and novel predatory strategies would redefine survival in a rapidly changing world. Sabres before the cat in Austransevere, Gorgonopsian. Emerging from the twilight of the Permian, a new predator moves with a lethal elegance that contrasts with the lumbering rulers before it. Austransevere prowled the late Permian forests and floodplains of what is now Russia, South Africa, and Eastern Europe. A predator designed not for brute domination, but for precision and speed. Measuring up to 3 meters in length, it carried an agile, elongated body built to strike swiftly and vanish, a radical departure from the open terrain authority of Dimetrodon. Its appearance signals a pivotal evolutionary moment where apex predation shifted toward refinement. Long, saber-like canines, reinforced skulls, and tightly coiled musculature allowed it to penetrate thick hides with lethal efficiency. Here, evolution experiments with surgical lethality, producing a predator whose success depends as much on skill as on strength. Coiled muscle along its neck hints at the terrifying power that drives elongated canines into the flesh of prey. The cervical vertebrae of Austransevere are remarkably reinforced, supporting repeated downward strikes capable of incapacitating prey before a struggle escalates. Fossilized remains suggest a predator able to control bite depth and angle with exceptional precision, an adaptation that made it a specialist hunter of large amphibians, early reptiles, and even smaller synapsids. The muscular attachments, preserved in fine detail through osteological markers, reveal a neck built like a loaded spring, storing energy to unleash sudden, devastating force. Inside the skull, reinforced bone and specialized sutures enable jaw strikes that maximize penetration without structural failure. The upper jaw housed long, laterally compressed canines, up to 20 centimeters in adult specimens, while the lower jaw offered support for swift closure and control. Biomechanical models indicate that these fangs could pierce through tough dermal armor and thick hides, emphasizing precision over brute-crushing power. Unlike Dimetrodon's open bite dominance, Innostransavia relied on targeted strikes, using its elongated canines almost like scalpels, delivering lethal efficiency while minimizing energy expenditure. Extending stealthily through the shadowed underbrush, limbs execute controlled lunges that reflect adaptations for sudden ambush. Its forelimbs and hindlimbs are proportioned to allow rapid bursts of speed across uneven terrain, while a flexible spine adds subtle torsion for balance during predatory strikes. Fossilized trackways indicate crouched stalking and rapid launch distances, suggesting that Innostransavia could approach undetected before delivering a precise, fatal bite. Its hunting technique required careful calculation and anatomical optimization, combining stealth, speed, and strike accuracy in a way that echoes the tactical predation of modern big cats, long before mammals ever evolved. Cranial measurements and biomechanical models reveal bite forces capable of crushing cartilage and rending sinew, targeting both large amphibians and early reptiles. Tooth wear patterns show repeated use on resisting prey, while skull reinforcements prevent catastrophic damage during violent struggles. Innostransavia could dispatch prey efficiently without overexerting itself, conserving energy for survival in a world of fluctuating resources. Its evolutionary success demonstrates the power of specialization, a predator perfectly tuned to exploit the vulnerabilities of contemporaneous vertebrates, outmatching larger but less precise competitors. Scattered vertebrate remains show evidence of selective predation, indicating a strategy combining opportunism with targeted efficiency. Fossil assemblages include bite-marked bones from amphibians, early reptiles, and even smaller gorgonopsians, revealing both predatory range and adaptability. While its elongated canines specialized it for certain prey, Innostransavia remained opportunistic when circumstances required, balancing precision and versatility. This dual approach allowed it to dominate terrestrial niches, even as ecosystems shifted, foreshadowing the selective pressures that would drive post-Permian predators toward agility and cunning over sheer mass. In the late Permian ecosystem, Innostransavia's presence influences the behavior, habitat selection, and evolution of coexisting species. Smaller reptiles adopted nocturnal habits or burrowing behavior to avoid encounters, while amphibians altered breeding and migration patterns to minimize predation risk. The gorgonopsian's predatory influence cascaded through the ecosystem, enforcing spatial and temporal partitioning that reshaped the lives of countless contemporaneous species. Its role demonstrates how apex predators can sculpt evolutionary trajectories beyond immediate prey populations, setting the stage for future ecological interactions. Fossil evidence of tooth wear, broken canines, and healed injuries suggests repeated encounters with large, struggling prey, highlighting both risk and skill. Innostransavia was not invulnerable. Successful predation demanded precision and resilience. Injuries preserved in skeletal fossils hint at clashes with large amphibians or other formidable prey, requiring the predator to refine its techniques continually. Each healed fracture or worn fang tells a story of survival, teaching us that mastery of lethal efficiency came at a cost, even for apex hunters. Subtle adaptations in limb musculature and spine flexibility allow rapid strikes while stabilizing the body for lethal precision. Its hindquarters enabled rapid directional shifts mid-attack while the forelimbs braced against struggling prey. This combination of anatomical refinement and biomechanical integration made it an apex predator that relied as much on skill and timing as on force. Inostrancevia exemplifies a shift from overwhelming power to calculated lethality, a crucial evolutionary experiment in the diversification of terrestrial hunters. Juxtaposed with earlier apex predators, Inostrancevia represents a refinement of killing tools and behavior, emphasizing speed, ambush, and accuracy over raw size. Its predecessors, like Dimetrodon, dominated through mass and raw force. Inostrancevia advantage lay in precision and adaptation to shadowed environments. This predator marks a pivotal moment where natural selection favored specialized morphology and sophisticated hunting strategies, a prelude to mammalian carnivores millions of years later. Each saber-like canine, elongated jaw, and reinforced neck vertebra tells a story of evolution honing specialization for survival on the brink of ecological collapse. In the Permian's final millennia, ecosystems teetered under climatic stress, habitat fragmentation, and resource scarcity. Inostrancevia thrived by exploiting ecological gaps with surgical efficiency, demonstrating that apex predation could be both strategic and deadly, not just overwhelming. Its anatomy, behavior, and hunting style are living evidence of evolution's capacity to refine predators for maximum effect in challenging worlds. On the brink of Permian catastrophe, these hunters illustrate both the peak of pre-extinction predatory sophistication and the fragility of ecosystems in the face of mass upheaval. Inostrancevia reign, terrifying in its precision and deadly elegance, stands on the cusp of extinction events that would obliterate the old order. Yet within the survivors of this collapse lies the blueprint for future predators, smaller, faster, and adaptable opportunists that will inherit a reshaped world. From these shadows, evolution sets the stage for terrestrial killers whose efficiency and agility will eclipse brute dominance, shaping the unfolding story of life on land. The burrowed survivor, Thrynaxodon. From the ruins of a world decimated by Permian catastrophe, a small shadow slips through cracked earth and sparse vegetation. Thrynaxodon, a diminutive cynodont measuring barely half a meter in length, navigates a landscape scarred by extinction. Vegetation is patchy, rivers meander as thin lifelines, and the air carries the smell of scorched soil. Yet within these fragile environments, survival demands ingenuity. Thrynaxodon embodies evolutionary resilience, small, nimble, and able to exploit niches abandoned by the obliterated giants of the late Permian. Its emergence is a testament to the subtle power of adaptability in a world stripped of abundance. Burrows excavated in compacted soil reveal a predator engineered for concealment and endurance in a harsh, unstable environment. Fossilized burrows in South Africa display evidence of carefully dug tunnels, complete with chambers that protected juveniles and offered temporary refuge from larger predators and harsh climate conditions. Limb morphology, strong forearms with robust claws allowed it to burrow efficiently, while its spine and flexible body facilitated movement through narrow tunnels. These structures were not mere refuges. They were hunting platforms, providing stealth and ambush opportunities for small, opportunistic prey. Hidden in the compact skull, teeth arranged for puncturing and slicing suggest a diet that included insects, small vertebrates, and scavenged carcasses. Dental morphology reveals a combination of sharp incisors for piercing soft-bodied prey and posterior teeth capable of crushing exoskeletons. This dietary versatility allowed Thrynaxodon to exploit any available food source, a crucial adaptation in an ecosystem recovering from global devastation. Fossilized coprolites confirm the ingestion of small vertebrate bones and insect remains, illustrating a predator that combined active hunting with opportunistic scavenging. Limbs adapted for digging and lateral motion allow precise control of movement underground and rapid escape on the surface. The forelimbs, with powerful flexor muscles, enabled thrusting through compacted earth, while hind limbs facilitated short bursts of terrestrial speed. Trackway analysis suggests agile terrestrial locomotion, enabling it to exit burrows quickly in pursuit of prey or to evade larger predators. Its body plan reflects a dual-purpose design, optimized for both subterranean survival and surface-level hunting. Traces carved into sediment reveal hints of communal living and interactions, behaviors previously unknown in small cynodonts. Evidence of multiple individuals within single burrow systems suggests cooperative or at least tolerantly cohabited spaces, perhaps enhancing survival in a precarious environment. This behavior hints at complex social dynamics, including parental care and potential early forms of communication or territory defense, adding a new dimension to the evolutionary story of early mammals. Juvenile and adult remains found together suggest a structured survival strategy, blending protection with opportunistic feeding. Young Thrinaxodon were not left to fend for themselves. Fossil associations indicate that adults likely guided juveniles to safer burrow chambers while still maintaining access to food sources. Such strategies reflect both evolutionary prudence and adaptability, reinforcing the predator's resilience in the face of extreme ecological pressure. Post-extinction scarcity influenced predatory behavior, pushing Thrinaxodon to exploit both living prey and carrion with equal skill. Opportunistic feeding allowed it to thrive where larger, more specialized predators could not. Fossil evidence shows gnawed remains of other small vertebrates, implying scavenging and occasional competitive displacement. This dietary flexibility ensured survival through resource fluctuations, demonstrating that adaptability often outweighs raw size in post-catastrophe ecosystems. Analysis of limb and spine morphology shows a delicate balance between subterranean navigation and terrestrial foraging. Its vertebral column exhibits flexibility that accommodates twisting, turning, and sudden directional changes in confined burrows, while joint articulation supports quick lunges and agile surface movement. This combination of anatomical adaptations makes Thrinaxodon a versatile predator, capable of responding to both environmental challenges and prey unpredictability. Evidence of wear patterns on teeth and claw marks within burrows provides a record of repeated survival strategies against environmental pressures. Dental microwear demonstrates frequent insect and small vertebrate consumption, while claw impressions indicate persistent excavation for shelter and ambush hunting. These physical records trace the daily rhythms of a predator navigating scarcity, revealing how anatomy and behavior co-evolved to create efficiency, resilience, and survival mastery in a volatile landscape. In the new Triassic ecosystems, small opportunists like Thrinaxodon pave the way for the diversification of predators capable of reclaiming open land. Though diminutive compared to Permian giants, these survivors introduced behavioral and anatomical innovations that influenced future lineages. Burrowing behavior, dietary versatility, and cooperative den use became evolutionary templates for subsequent cynodonts, illustrating that survival in collapse-driven ecosystems depends on adaptability as much as predatory skill. Each anatomical adaptation, from reinforced skull to flexible limbs, tells the story of survival and subtle predatory dominance in a world recovering from mass extinction. Thrinaxodon thrived not by brute force, but through clever use of terrain, burrows, and opportunistic feeding. In doing so, It bridges the evolutionary gap between the apex predators of the Permian and the more specialized hunters of the Triassic, preserving the predatory lineage through a period of profound ecological upheaval. Survivors burrow below, but above them, archosauriform predators rise, ready to dominate the lands abandoned by extinct giants. Thranaxodon's ingenuity, adaptability, and cautious predation reflect a transitional era. Small, agile predators filling ecological voids, while evolution quietly prepares the next generation of killers. Its legacy reminds us that survival is as much about flexibility, resilience, and strategy as it is about size or strength, and that in the wake of destruction, the smallest predators often sow the seeds of future domination. The crocodile that walked upright, Proterosuchus. Sunlight glints off shallow river channels as a long-bodied predator slinks along the banks with lethal precision. Proterosuchus, an early archosauriform spanning roughly 2 meters in length, moves with a grace that belies its bulk. The post-Permian landscapes it inhabits are open, sparse, and harsh, shaped by a world still recovering from mass extinction. Yet these empty floodplains and riverbanks provide a new hunting ground where opportunistic predators like Proterosuchus exploit every advantage. Its semi-upright posture and swift reflexes transform the shallow waterways into stages for deadly ambushes, demonstrating that land, once perilous, has become a domain of predatory possibility. Muscle attachments along its limbs and spine reveal adaptations for semi-upright locomotion, allowing sudden lunges on land. Fossil evidence of limb and girdle structure shows a transitional gait capable of both sprawling movement and short bursts of more erect steps. These mechanics enabled Proterosuchus to strike with precision, lunging at unsuspecting prey along river margins or across floodplain mud. The combination of aquatic maneuverability and terrestrial agility made it one of the first predators to exploit multiple environments simultaneously, a precursor to the fully land-committed archosaurs that would later dominate. Designed for precision, the lightly built skull bears conical teeth that grasp struggling prey instead of crushing bone. Unlike the bone-crushing jaws of Permian synapsids, Proterosuchus relied on swift bites to immobilize rather than pulverize. Its tooth arrangement, coupled with a narrow snout, allowed for efficient capture of small vertebrates emerging from water or fleeing along the banks. Paleontologists studying cranial fossils note both the leverage mechanics and jaw flexibility, revealing an animal engineered for opportunistic strikes with minimal expenditure of energy, a subtle but lethal efficiency that defines early Triassic predation. Trackways, preserved in sedimentary deposits, demonstrate both terrestrial and shallow water movement, highlighting hunting versatility. Fossilized footprints reveal gait patterns alternating between sprawling strides near river shallows and semi-upright lunges across exposed floodplains. These traces provide a tangible record of behavior, showing a predator attuned to its environment and capable of exploiting terrain to its advantage. In combination with burrowing survivors like Thranaxodon, Proterosuchus illustrates the growing complexity of post-extinction ecosystems, where predator and prey interact across multiple ecological layers. Vertebral morphology supports both lateral flexibility for aquatic maneuvering and torsion required for land-based strikes. Its backbone demonstrates a delicate compromise, allowing sufficient twisting to catch prey in water while maintaining stability for sudden terrestrial lunges. Such adaptations reflect a predator still anchored to aquatic origins, yet increasingly confident on land, presaging the gradual rise of fully terrestrial hunting strategies in later archosaurs. Riverside ambushes exploit both terrain and water, showing early archosauriform ingenuity in bridging aquatic and terrestrial hunting. Proterosuchus would lurk near the water's edge, exploiting the mirrored reflection of unsuspecting prey or the uneven mudflats where small vertebrates paused to drink. Its hunting method reflects an early understanding of environmental advantage. Concealment, timing, and precise lunges combine to secure meals without protracted struggle. Here, predation becomes a blend of instinct, anatomy, and spatial awareness, a harbinger of more deliberate strategies that will define future land predators. Fossil evidence suggests rapid growth rates and metabolic efficiency, allowing sustained predatory activity in unstable post-extinction ecosystems. Bone histology reveals a combination of fast maturation and flexible physiology, enabling prolonged hunting periods across riverine and terrestrial landscapes. These traits were critical in the early Triassic, when food scarcity and environmental volatility demanded resilience and efficiency. Proterosuchus's success demonstrates that evolutionary innovation often emerges most clearly in times of ecological stress. Interactions with smaller vertebrates indicate calculated predation, balancing risk with energy expenditure during hunts. Coprolite analysis and bite-marked fossils show that Proterosuchus targeted species, from surviving amphibians to small cynodonts, choosing prey that offered sufficient caloric return for minimal risk. This behavior marks a subtle shift from indiscriminate consumption toward selective hunting, a trait that will become increasingly sophisticated in archosaur lineages, culminating in the predatory strategies of early dinosaurs. The skeletal structure hints at a predator evolving toward greater independence from water, foreshadowing later fully terrestrial killers. Limbs, hips, and vertebrae reveal adaptations that allow extended terrestrial excursions with bursts of speed and lunging attacks along open floodplains. Proterosuchus demonstrates that even in an era dominated by recovering amphibians and opportunistic cynodonts, larger, semi-upright predators could exploit land as both hunting ground and refuge, further shaping the post-extinction ecosystem. Each claw impression, tooth mark, and fossilized footprint provides insight into hunting behavior, ecological dominance, and environmental adaptation. By combining observational paleontology with biomechanical modeling, scientists reconstruct a predator that is both versatile and efficient. These small details embedded in stone allow us to imagine the silent stalking along riverbanks, the sudden lunge at a fleeing prey, and the careful retreat into shaded shallows, a dance of life and death recorded across millions of years. In occupying open riverine landscapes, Proterosuchus establishes niches that will be contested and expanded by subsequent Triassic predators. Its presence demonstrates the possibilities of semi-terrestrial predation, bridging the gap between small opportunists and future archosauriform apex predators. With each successful strike, it not only secures sustenance, but also sets the evolutionary stage for increasingly sophisticated terrestrial killers, shaping the trajectory of predator-prey dynamics for generations to come. With ecosystems stabilizing, the emergence of deliberate, large-scale predators follows the success of early archosauriforms. Proterosuchus embodies the tension between aquatic ancestry and terrestrial ambition, illustrating the careful experimentation of evolution as predators explore new forms, strategies, and terrains. Its combination of agility, precision, and opportunistic intelligence ensures that open land will no longer remain a passive stage but becomes a theatre for hunting, laying the groundwork for the first calculated, truly land-dominant killers, the archosaurs that will redefine predation in the Triassic. the first dinosaur predator Herrerasaurus. Dust rises along the sun-baked forest floor as a lean predator threads between ferns and cycads, silent yet deadly. Herrerasaurus, one of the earliest true dinosaurs, embodies an evolutionary leap, a predator fully committed to land, agile, and precise in its movements. Its long, lightly built frame allows for bursts of speed across uneven terrain, transforming the Triassic forest floor into a stage for rapid, calculated predation. In a world still recovering from the Permian-Triassic collapse, every shadow, every rustle of leaf litter becomes a potential opportunity or threat. Unlike its semi-upright archosauriform predecessors, Herrerasaurus moves with confidence, each step measured, each lunge deliberate. Judging from the muscle attachments along the femur and pelvis, this predator could achieve impressive stride length and rapid, short sprints. Paleontologists examining fossilized limb bones reveal that this predator could achieve sudden bursts of speed to close gaps with fleeing prey, a stark contrast to the slower, ambush-oriented lunges of Proterosuchus. The limbs, combined with a balanced tail, provide both stability and flexibility, essential for navigating the uneven forest floor or sprinting across open clearings. Such locomotor refinement marks a decisive step toward the energy-efficient, pursuit-oriented predation that will define later theropods. Its recurved claws, finely serrated and flexible, allow for precision, gripping, and tearing, a design perfected for killing rather than scavenging. Each claw, though small relative to the body, functions as a scalpel in the predator's hands, or rather, feet, ensuring prey cannot escape once grasped. Fossilized bones of small archosaurs and early herbivores bear the marks of these lethal tools, demonstrating targeted strikes and controlled predation rather than random consumption. Herrerasaurus exemplifies the first dinosaurs whose anatomy emphasizes efficiency, speed, and lethality in equal measure. The jaw, lightly constructed but armed with slicing teeth, reflects an evolutionary commitment to efficiency over brute force. Unlike Permian apex predators, whose jaws were adapted to crush or immobilize with sheer power, Herrerasaurus relies on swift, precise bites. Serrated teeth cut through flesh and muscle, allowing for rapid incapacitation of prey while conserving energy, a necessity in a world where hunting success is not guaranteed. This combination of light skull construction and effective dentition demonstrates an early optimization of form and function in terrestrial predation. Imprinted in ancient trackways is proof of agility, balance, and sudden turns, showcasing a predator no longer bound by semi-aquatic constraints. Herrerasaurus navigated forests and floodplains with remarkable dexterity, weaving between trees and leaping over fallen logs in pursuit of its quarry. Footprint spacing reveals stride lengths and pacing consistent with an animal capable of sudden accelerations, demonstrating that the evolutionary experimentation of earlier archosauriforms has culminated in a creature fully adapted to deliberate, land-based hunting. Prey remains, including juvenile sauropodomorphs and small archosauriforms, reveal targeted hunting and selective consumption. Herrerasaurus demonstrates discernment in prey choice, favoring targets that maximize caloric intake relative to effort and risk. Bite marks show clean, repeated strikes, reflecting calculated predation rather than opportunistic feeding. Its hunting behavior signals a shift towards specialization, where speed, strategy, and anatomical precision define success. Posture and vertebral articulation suggest an evolved center of gravity optimized for sprinting across uneven terrain. Unlike sprawling or semi-upright predecessors, Herrerasaurus's vertebral column and pelvic structure allow for an efficient, balanced gait. This anatomical refinement reduces energy expenditure during high-speed pursuit, enabling sustained predatory activity in challenging Triassic landscapes. Here, evolution demonstrates the elegance of adaptation. Form perfectly tuned to function. Speed married to stability. Environmental reconstructions show Herrerasaurus exploiting both open clearings and shaded woodlands, maximizing hunting opportunities across landscapes. Its presence in multiple microhabitats highlights ecological versatility, allowing it to hunt both in the open and among dense vegetation. By mastering these contrasting environments, Herrerasaurus not only secures survival, but also asserts dominance over prey species and smaller competitors, shaping the early Mesozoic food web. Comparative analysis with contemporary predators highlights the transition from opportunistic ambushes to active pursuit predation. Where Proterosuchus and similar archosauriforms relied on proximity and surprise, Herrerasaurus incorporates speed, precision, and environmental awareness to dictate the terms of engagement. This behavioral sophistication foreshadows the rise of later theropods, where coordinated stalking, pursuit, and even potential social hunting dynamics will define predatory efficiency. Bone microstructure indicates rapid growth and high metabolic demands, sustaining prolonged activity and energetic hunts. Histological studies of limb and vertebrae fossils reveal that Herrerasaurus could sustain bursts of activity with minimal fatigue, an advantage in pursuing swift or evasive prey. These physiological adaptations mark a departure from the slower, less energetically optimized hunting strategies of early Triassic predators. Claw and tooth wear patterns suggest repeated use in precise strikes, not random tearing, demonstrating controlled predation strategies. These marks indicate a predator with learned behavior and anatomical specialization, targeting vulnerable points in prey anatomy to maximize efficiency and minimize risk. Herrerasaurus embodies the first predator whose body and behavior are honed for calculated killing, a blueprint for all dinosaurs that will follow. By the end of its active hunting cycle, Herrerasaurus establishes itself as a paradigm of terrestrial predatory innovation, influencing the trajectory of Mesozoic killer lineages. Its agility, slicing jaws, and precision claws not only redefined predation in the Triassic, but also set evolutionary expectations for what terrestrial hunting can achieve. As ecosystems grow more complex, Herrerasaurus demonstrates that speed, intelligence, and strategic anatomy can outweigh brute strength, heralding a future where lean, deliberate, and highly efficient predators dominate the Mesozoic landscape, foreshadowing the rise of social and larger-bodied dinosaur killers that will further transform land-based hunting. The ghost of the bone beds Coelophysis. Sliding silently between sun-dappled clearings, Coelophysis moved with a grace that belied its lethal intent. A predator whose slender frame and long legs allowed it to navigate the fluctuating terrain of Triassic floodplains with both speed and stealth. Fossil evidence shows that these small dinosaurs hunted not only reptiles and early mammals, but also their own kind, leaving behind a chilling record of cannibalism that hints at the brutal realities of survival in a resource-limited world. Their recurved, serrated teeth, perfectly designed for slicing soft tissue, mark them as efficient killers, while their lightweight skeletons enabled sudden bursts of acceleration, turning ambush into an art perfected by evolutionary experimentation. The skeletal record whispers of repeated violence, with fossilized assemblages revealing groups of Coelophysis that died together, suggesting that these predators were not solitary hunters, but operated in packs or loosely coordinated social units. Such evidence challenges assumptions about early dinosaur behavior, showing that social predation strategies emerged far earlier than previously thought. Within these bone beds, juveniles, subadults, and adults intermingle, hinting at complex interactions ranging from cooperative hunting to opportunistic cannibalism, a grim testament to survival pressures that shaped both behavior and anatomy. Tooth-marked remains reveal ruthless opportunism, with partially eaten conspecifics suggesting that hunger could override instinctive restraint. In the harsh and fluctuating Triassic climate, resources were often scarce, and efficiency dictated evolutionary success. Coelophysis' ability to exploit every available food source, whether small reptiles, mammals, or even weakened pack members, demonstrates the versatility required of predators navigating post-extinction ecosystems. Their behavioral flexibility, paired with anatomical adaptations, positioned them as formidable agents in the reconstruction of terrestrial food webs. Elongated hind limbs and limbs designed for sudden bursts allowed predators to accelerate rapidly, while the rigid tail ensured stability during high-speed turns. This combination allowed coelophysis to close the distance between hunter and prey in mere seconds, striking with accuracy that would make larger, slower predators envious. Forelimbs, though modest in size, offered control over struggling prey, while sensory adaptations, keen vision, and enhanced spatial awareness ensured that even subtle movements could betray the presence of potential meals or rivals. Coordinated strikes transform open land into lethal traps, as pack members work together to herd prey toward ambush points or outflank their quarry. This level of strategic sophistication, rare for predators of their size, demonstrates that evolutionary pressures favored not only anatomical refinement, but also social intelligence. By moving collectively, coelophysis could increase the odds of a successful hunt, particularly against fast or evasive prey, and could even dominate territories shared with other small predators. Such behavior laid the groundwork for future Mesozoic predators, whose strength would combine physical prowess with social coordination. Hunting strategies rely as much on timing as on individual skill, with each strike and maneuver executed in synchronization with pack movements. Fossilized footprints and trackways, though rare, hint at coordinated chases and group formations that allowed these slender hunters to exploit the terrain to their advantage. In the unpredictable landscapes of the late Triassic, the ability to combine speed, precision, and group tactics became a decisive evolutionary trait, distinguishing coelophysis from solitary contemporaries and marking a turning point in terrestrial predation. Seasonal floods, shifting river channels, and fluctuating prey populations shaped both anatomy and predatory behavior, demanding versatility from these hunters. Coelophysis had to adapt to both open plains, where visibility was high, but escape routes were numerous, and wooded margins, where stealth and ambush were more effective. Such selective pressures favored lightweight frames, elongate limbs, and keen sensory adaptations, shaping a predator that was not only efficient, but also highly adaptable to environmental change. Cannibalistic tendencies highlight survival in scarce ecosystems, a grim reminder that in extreme conditions, predation extends even to one's own species. Tooth marks on bones of conspecifics, coupled with evidence of repeated pack deaths, indicate that coelophysis could exploit every possible resource when food was limited. This behavior underscores the delicate balance between cooperation and competition within early social predators, illustrating that evolutionary success depended on a flexible approach to both prey and peers. Packs sharpen evolutionary edges as the combination of coordinated hunting, anatomical specialization, and opportunistic feeding amplified selective pressures on speed, intelligence, and group cohesion. Fossils from multiple localities suggest that these dynamics were consistent across wide geographic ranges, emphasizing the role of social predation in shaping early dinosaur evolution. Through this lens, Coelophysis becomes more than a solitary killer. It emerges as a formative model of what terrestrial predators could achieve when anatomy, environment, and social strategy converged. In this world of Triassic tension, larger predators loom on the horizon as the lessons learned in coordinated hunting, speed, and opportunistic behavior set the stage for the evolution of species with bone-crushing power, massive size, and dominance over entire ecosystems. Coelophysis, in its slender, ghostly form, demonstrates that efficiency, agility, and intelligence could rival brute strength, and its legacy would echo in the predators that soon emerged to dominate the Mesozoic landscapes, with jaws built to split bone and claws, designed for supremacy. Twin crests of death, Dilophosaurus wetherilli. Forest shadows conceal the looming silhouette of a predator, a creature whose elongated limbs and towering frame allow it to stalk the early Jurassic woodlands with calculated intent. Dilophosaurus moves with a balance of strength and grace, its twin cranial crests rising like visual flags, possibly signaling dominance, species identity, or sexual selection, though their precise function remains debated. Its presence in the fossil record, articulated skeletons and associated trackways, reveals a predator capable of explosive bursts of speed across uneven terrain, transforming river margins and forest edges into hunting theatres where prey had little chance of escape. The environment itself, a mosaic of seasonal floodplains, meandering streams, and dense fern and conifer thickets, demands versatility. A predator must negotiate muddy banks, fallen trees, and undergrowth while remaining unseen until the strike. Twin crests rise like banners above a deadly frame, marking an evolutionary shift toward larger, more physically imposing predators. Unlike the slender Coelophysis that navigated open landscapes with subtlety, Dilophosaurus possesses reinforced limb bones and powerful musculature, engineered to sustain repeated lunges against prey far larger than itself. Its teeth, serrated and recurved, could pierce thick hides, tear flesh, and stabilize struggling victims, demonstrating that evolution had moved beyond mere speed and opportunism to the design of calculated, lethal force. Each anatomical innovation, from jaw articulation to vertebral flexibility, reflects a predator increasingly capable of dominating complex, three-dimensional habitats, exploiting terrain that earlier Triassic predators could only cautiously traverse. Energy-packed muscles beneath the scales unleash rapid accelerations, allowing the predator to strike unsuspecting prey with devastating force. The hind limbs, elongated and robust, work in concert with tail counterbalance, allowing precise directional control during high-speed pursuits. Forelimbs, though modest relative to the body, assist in grappling or pinning prey, while strong cervical musculature enables rapid head strikes and powerful bites. In addition, the shoulder girdle and pectoral muscles suggest significant upper body strength, allowing Dilophosaurus to maintain grip on large prey while positioning for a fatal bite. Together, these features create a predator built for both endurance and instantaneous bursts of energy, a combination that reshapes the possibilities of terrestrial killing. Massive jaws snap with the precision of a well-oiled machine, capable of inflicting fatal damage in a single strike. Biomechanical modeling of jaw strength suggests that Dilophosaurus could crush bone in smaller prey and deliver lethal bites to larger animals, a capability unprecedented among its Triassic predecessors. The dentition, serrated and laterally compressed, slices cleanly through tissue while maintaining the structural integrity necessary for repeated use, illustrating an evolutionary design optimized for both power and efficiency. Microscopic wear patterns on teeth suggest repeated use on both soft tissue and tougher, fibrous material, indicating a predator unafraid to tackle varied prey in a dynamic ecosystem. Adapted for force and agility, the limbs carried the predator over complex terrain, keeping it effective amid logs, rivers, and thick undergrowth. Fossilized trackways hint at both solitary movement and occasional group behavior, suggesting that these predators could exploit both ambush and pursuit strategies depending on terrain and opportunity. Their presence shifts the ecological balance, compelling prey species to develop defensive behaviors such as rapid evasive movement, camouflage, and early warning systems, while heightening competition among contemporaneous predators. This dynamic interaction between predator and prey emphasizes the role of Dilophosaurus not merely as a hunter, but as a driving force shaping evolutionary trajectories across multiple species. Prey species scatter, testing the predator's tactical ingenuity as Dilophosaurus selects targets with a combination of instinct, learned behavior, and opportunistic precision. Early ornithischians, small synapsids, and juvenile sauropodomorphs provide both challenge and sustenance, their reactions shaping the predator's hunting techniques over evolutionary time. Some evidence even suggests selective targeting of weakened or isolated individuals, indicating a capacity for risk assessment and adaptive hunting. This interplay between hunter and hunted demonstrates how anatomical innovation, powerful limbs, muscular jaws, and sensory acuity interacts with environmental pressures to refine predation into an art form, echoing in future theropod lineages. Cranial morphology and bone structure highlight a history of evolutionary trade-offs, weighing speed against bite force and skull strength. The dual crests, though delicate compared to the jaw and limb apparatus, may have played roles in thermoregulation, social signaling, or sexual display, highlighting the interplay between survival function and social dynamics. These subtle features remind us that evolutionary success relies not solely on brute force, but on an integrated suite of adaptations that enhance both hunting capability and reproductive success. Furthermore, the vertebral column, with its enhanced zygapophyses and interlocking processes, suggests a spine capable of absorbing the stresses of high-speed strikes and twisting motions during prey capture. Both solitary and collaborative hunting appear in tracks and fossil evidence, though the details of social interactions remain unresolved. Some trackways suggest sequential movement, where one individual follows the path of another, potentially indicating hunting in loose association or strategic positioning to outflank prey. Such evidence, combined with anatomical adaptations for speed and power, positions Dilophosaurus as a predator that could dominate early Jurassic ecosystems through both mechanical efficiency and behavioral sophistication. Its hunting strategies, whether ambush, pursuit, or opportunistic exploitation, illustrate the ways predators adapt to environmental complexity and prey diversity. Dense vegetation challenges both hunter and hunted, shaping movement, strike angles, and attack timing. Riverine and forested habitats require constant adjustment, and the predator's anatomical design reflects these constraints. A flexible spine, long stride, and balanced center of mass enable navigation without losing predatory efficiency. Its heightened senses, keen vision, and acute olfactory capability further facilitate hunting in low-light conditions beneath the forest canopy, suggesting that Dilophosaurus could stalk prey across both open and covered terrain. These adaptations illustrate the ongoing arms race between predator and prey, a cycle that drives morphological and behavioral innovation across successive generations. Within these forests, a new scale of predation asserts dominance, signaling that size, power, and refined anatomy now command the landscape. Dilophosaurus demonstrates that evolutionary success in terrestrial predators hinges not only on the ability to kill, but on the capacity to exploit ecological opportunities, integrating speed, strength, and environmental mastery. Its reign foreshadows a future where Mesozoic predators will grow ever larger, more specialized, and increasingly capable of reshaping entire ecosystems with their hunting strategies, ensuring that each innovation in prey and predator alike fuels an unending cycle of adaptation and escalation. The forest executioner, Allosaurus fragilis. Moving through open floodplain glades, Allosaurus casts a shadow over the grazing stegosaurs below, muscles coiled for the precision and speed required to transform vegetation-rich plains into hunting grounds. Each stride demonstrates a predator honed for repeated attacks, its body a synthesis of endurance and explosive power. The Morrison ecosystems, with their seasonal rivers, open clearings, and dense fern understories, demand both adaptability and patience. Any misjudged step could alert prey, while terrain can serve as an advantage for a predator built to exploit it. Fossil evidence reveals that Allosaurus operated in landscapes crowded with herbivores ranging from bulky sauropods to nimble ornithischians, and its anatomical evolution reflects an arms race where power, accuracy, and efficiency became paramount. Allosaurus's scaly skin conceals muscles built for explosive speed, allowing repeated bursts of acceleration and highly accurate strikes. The hind limbs, elongated and reinforced, provide both stride and leverage, allowing the predator to lunge and reposition with calculated grace. Its tail serves as a counterbalance during these maneuvers, enhancing stability and directional control, while the forelimbs, though smaller relative to the body, are heavily muscled and capable of grappling, holding prey in place for fatal bites. This combination of limb coordination, spinal flexibility, and tail dynamics demonstrates a predator optimized for repeated, high-impact predation over complex terrain. Teeth, serrated and recurved, lock into bone and tear with remarkable resilience, reflecting evolutionary pressures to hunt large, heavily armored prey. Microscopic wear patterns reveal repeated use against tough, fibrous tissue, suggesting that Allosaurus was capable of inflicting lethal damage without compromising its dentition. Its jaws, reinforced with robust cranial bones, absorb the stress of high-force strikes while maintaining accuracy, illustrating a balance between power and repeated functional use. Each bite could puncture rib cages, sever vertebrae, or tear muscle from bone, an efficiency that signals a predator at the peak of mechanical and anatomical adaptation in its era. Forelimbs, though proportionally smaller than the hind limbs, provide control during grappling and stabilizing prey, allowing Allosaurus to combine precision with brute force. Claws, sharp and recurved, anchor into flesh or secure struggling prey while the jaws complete the kill. This synergy between limbs, claws, and jaws demonstrates an evolutionary strategy in which multiple anatomical systems cooperate to maximize predation efficiency. Evidence from fossilized skeletons and trackways indicates that these predators could repeatedly strike, reposition, and continue attacks, demonstrating both endurance and tactical intelligence. Seasonal rivers carve the landscape, creating both hunting grounds and obstacles that shape predatory strategies. Floodplains, with soft mud, fallen trees, and shifting channels, demand precise limb placement and flexibility to maintain stealth and acceleration. Allosaurus's vertebrae, featuring interlocking zygapophyses, provide a spine resilient to torsional stress, absorbing the repeated forces of lunges and lateral strikes. Its balance of power and flexibility allows it to hunt in open areas and near vegetative cover alike, converting environmental complexity into a predatory advantage. Internal musculature and cardiovascular adaptations enabled Allosaurus to sustain repeated bursts of high-intensity activity across the floodplain. The caudal and dorsal musculature, anchored along elongated neural spines, functioned like hydraulic springs, storing and releasing energy with each stride or lunge, while the respiratory system, inferred from rib and sternal anatomy, suggests efficient air circulation capable of supporting both endurance and sudden exertion. Bone microstructure indicates dense yet lightweight construction, reducing overall energy expenditure without compromising strength, allowing Allosaurus to maintain lethal force over extended hunting sessions. Such integration of muscular, skeletal, and cardiovascular systems highlights how its body functioned as a finely tuned predatory machine, converting raw strength into sustained, precise, and adaptable action across complex terrain. Sensory systems, from acute vision to finely tuned hearing, allow detection of subtle movement across dense terrain, giving Allosaurus the ability to time attacks with lethal precision. Binocular vision enables depth perception for judging distance and strike trajectories, while the auditory system detects minor rustlings that betray the presence of herbivores or potential competitors. These senses, integrated with muscular and skeletal adaptations, reveal a predator whose hunting capabilities extend beyond brute strength into the realm of calculated, adaptable intelligence. Healed injuries in prey fossils reveal repeated predation attempts, showing that Allosaurus relied not just on ambush, but could chase and persist against resilient targets. Bones bear marks of slicing teeth and claw gouges, indicating that even partially armored stegosaurs or juvenile sauropods were vulnerable to repeated attacks. This persistence, combined with anatomical optimization for endurance and repeated strikes, emphasizes the predator's role in shaping the evolutionary pathways of coexisting species. Social or opportunistic associations may have enhanced hunting success, though the full dynamics remain a matter of ongoing research. Fossil assemblages hint at sequential movement or group proximity, suggesting the possibility of coordinated hunting or scavenging strategies that would increase efficiency and prey acquisition. These behavioral inferences, while subtle, demonstrate that Allosaurus's predatory dominance may have combined physical prowess with strategic understanding of the environment and other individuals, further solidifying its apex status. The forest understory forces adaptive stride, flexible spinal control, and coordinated lunges that maximize hunting efficiency, illustrating how anatomical refinement and environmental mastery coalesce in a predator capable of repeated, lethal engagements. Dense vegetation channels movement and dictates angles of attack, demanding that precision and power be balanced against agility. Such integration of anatomy, strategy, and environmental adaptation allows Allosaurus to dominate its ecosystem, exploiting the interplay between terrain, prey behavior, and predator capability. Dominating Morrison ecosystems, Allosaurus showcases strength, rapid movement, and strategic hunting techniques. Its evolution exemplifies the culmination of a series of Mesozoic predatory experiments. A predator that balances repeated lethal efficiency with environmental adaptation, demonstrating that mastery of land-based hunting requires more than power alone. As forests thicken and prey strategies diversify, Allosaurus exemplifies how endurance, precision, and mechanical optimization reshape predator-prey dynamics, heralding the rise of even larger, more specialized killers whose influence will reverberate across the Jurassic landscapes. The spine-backed pursuer, Acrocanthosaurus attokensis. Following the legacy of Jurassic killers, Acrocanthosaurus enters a landscape dominated by towering prey and increasingly competitive predators. Its enormous frame, a testament to evolution's push towards sheer power, amplified by mechanical ingenuity. Stretching nearly 12 meters from snout to tail, its neural spines rise like jagged ridges along the back, forming a complex scaffold for muscle attachment that transforms simple mass into precise, sustained force. In the sun-scorched floodplains of the early Cretaceous, these predators move with an unexpected fluidity, their stride deceptively controlled for such immense size, demonstrating that predatory dominance is no longer solely a matter of strength, it is also a feat of biomechanical sophistication. Its towering neural spines, partially enveloped by dense musculature, create a living suspension system that stabilizes the body during repeated lunges and slashing attacks. Modern studies of related theropods suggest these spines allowed the predator to maintain balance while striking enormous herbivorous prey, distributing stress across vertebrae and limbs to prevent injury. Each movement, from lunging to pivoting, relies on this integration of skeletal and muscular architecture, transforming raw weight into a predator capable of sustained, high-force engagement. Fossilized forelimbs, reinforced with robust muscle scars and claw articulation, reveal that these structures were not passive supports, but active participants in capturing and subduing struggling prey. Across early Cretaceous floodplains, Acrocanthosaurus's gait exhibits an unusual combination of stability and power, with limbs that absorb impact while transferring energy to the spine. Trackway analysis shows stride lengths consistent with high-force locomotion, while preserved tail vertebrae suggest counterbalancing mechanisms that facilitated rapid acceleration during ambush. Unlike its Jurassic predecessors, this predator combines muscular amplification with spinal reinforcement, allowing it to hunt over longer distances and apply repeated pressure without succumbing to fatigue. Its anatomy embodies the evolutionary principle that larger size must be coupled with biomechanical efficiency to maintain predatory advantage. Powerful forelimbs, clawed and reinforced, coordinate with the neural spine to stabilize high-force lunges, permitting Acrocanthosaurus to grapple with prey many times its mass. The claws themselves are subtle instruments of death, capable of holding struggling herbivores long enough for the jaws to execute precise, crushing bites. Fossil evidence from partially eaten sauropodomorphs demonstrates patterns of skeletal trauma that align with this hunting method, revealing that the predator's physical design directly translates into ecological impact. Musculature along the neck and shoulders, attached to the spines, allowed repeated biting strikes without loss of precision, underscoring how anatomical innovation amplifies predatory efficiency. Skull morphology reveals a predatory apparatus finely tuned for sustained assault, teeth recurved and serrated, jaw muscles powerful yet shock-absorbing, and cranial architecture engineered to prevent fracture under repeated stress. These adaptations allow Acrocanthosaurus to target not only flesh but bone, applying lethal force that could incapacitate large ornithischians or armored herbivores. Bite force estimates, extrapolated from jaw musculature and leverage ratios, suggest an ability to crush bone while minimizing energy expenditure, a feat unmatched by most contemporary predators. Even small anatomical details, like reinforced cranial sutures, testify to a predator whose form evolved to endure extreme mechanical stress. Endurance hunting, enabled by energy-efficient locomotion and spinal reinforcement, distinguishes Acrocanthosaurus from earlier Jurassic predators that relied more on ambush than sustained pursuit. Its body functions like a finely tuned machine, converting each muscle contraction into forward momentum and precision striking power. This capacity for prolonged predation permits it to dominate prey across floodplains and riverbeds, exploiting herbivore herds with strategic calculation rather than mere opportunism. Environmental pressures, from soft sediment to flowing water, tested its stamina and stability, yet the predator's adaptations allowed it to master these challenges with minimal injury or fatigue. Evidence from trackways and prey fossils demonstrates that these structural innovations translate directly into ecological dominance. Patterns of injury in early Cretaceous herbivores indicate repeated slashing and grasping attacks, consistent with the predator's anatomical capabilities. Fossilized bite marks along vertebrae and limb bones reveal systematic subjugation of prey, suggesting that Acrocanthosaurus hunted with both power and precision rather than haphazard brutality. Its success reshaped predator-prey dynamics, forcing herbivores to adapt in speed, group behavior, and defensive morphology, a ripple effect of evolutionary pressure radiating across the ecosystem. Neural and muscular integration allows precise force distribution, maintaining efficiency over repeated strikes and sustained pursuits, highlighting the predator's role as an apex architect of ecological structure. Biomechanical modeling indicates that each spine acts as a conduit for energy, channeling force into the legs, tail, and forelimbs during high-stakes encounters. In combination with cognitive awareness, this predator could select targets, coordinate strikes, and maintain lethal efficiency in ways that earlier, less structurally complex theropods could not. Its dominance is as much a story of anatomical ingenuity as it is of raw size, emphasizing that the evolution of killing power is inseparable from the refinement of form. The early Cretaceous world reveals Acrocanthosaurus as a predator shaped by the interplay of brain, muscle, and bone, impacting ecosystems well beyond the animals it hunted. Each feature, from reinforced spines to energy-efficient stride, illustrates an evolutionary response to the demands of size, force, and ecological complexity. This fusion of biology and biomechanics not only ensures survival and predatory supremacy, but also sets a precedent for future Mesozoic hunters, where cognition, endurance, and structural design collectively define the limits of terrestrial killing. As ecosystems continue to diversify and competition intensifies, the next predators will inherit these lessons, blending speed, intelligence, and innovation to dominate in ways even more terrifying and efficient. The thinking predator, Trudon formosus. Building on the lessons of massive predators like Acrocanthosaurus, Trudon navigates late Cretaceous forests and floodplains with a precision born of intelligence rather than sheer size. Its lithe frame balances agility with efficiency, each stride calibrated to minimize energy while maximizing predatory reach. Unlike the lumbering tyrants of the same period, this small theropod relies on strategy, observation, and adaptive decision-making, proving that lethal success is not solely a matter of brute force. The predator's evolutionary design reflects a remarkable fusion of cognition, sensory acuity, and anatomical refinement, creating a hunter capable of outthinking its prey. In a world shaped by giant, high-powered hunters, Troodon represents an alternative path, one where brains amplify the effectiveness of muscle, strategy eclipses raw force, and the smallest predators can dominate through cleverness and coordination. In the shadowed undergrowth of late Cretaceous forests, every movement becomes a calculated decision. Rustling leaves, shifting shadows, and the faint tremor of a small mammal or lizard can trigger a sequence of rapid, coordinated motions executed with precision, honed over evolutionary time. Troodon's environment demands constant assessment, integrating visual, auditory, and olfactory inputs into split-second tactical choices. Whereas larger predators dominate by sheer intimidation or overpowering force, Troodon exploits subtleties, proving that predation can be governed by intelligence as much as by physicality. Its world is a theatre of perception, anticipation, and strategy, where each decision can mean success or failure in a densely vegetated, dynamic ecosystem. Enhanced auditory and visual systems reveal an acute awareness of surroundings, enabling detection of movement imperceptible to larger hunters. Binocular vision grants precise depth perception, allowing accurate calculation of distance, trajectory, and timing before committing to a strike. Fossil reconstructions indicate relatively large optic lobes and expanded cerebral hemispheres, suggesting a capacity for rapid processing of sensory input and decision-making under pressure. In combination with keen hearing and a refined sense of smell, Troodon could identify prey hiding under leaf litter, burrowing mammals, or even the subtle movements of a fellow pack member. This level of environmental literacy distinguishes it from other small theropods, demonstrating that intelligence itself can serve as a predatory multiplier. Braincase morphology further supports reasoning capabilities far beyond contemporaneous predators, enabling behaviors that required planning, patience, and adaptability. Troodon could assess risk, anticipate escape routes, and adjust strategies in real time, effectively thinking its prey into vulnerability. Comparisons with similarly sized theropods demonstrate that its encephalization quotient ranks among the highest in non-avian dinosaurs, a testament to a sophisticated cognitive toolkit. This intelligence allowed Troodon to exploit niches inaccessible to larger, stronger predators, carving a unique role in complex food webs where agility, foresight, and strategic decision-making outweighed brute strength. Dexterous forelimbs, paired with recurved, serrated claws, allowed for precise strikes and prey manipulation, turning hunting into a controlled, tactical engagement. Troodon could grasp, hold, and repeatedly attack smaller vertebrates, insects, and even the offspring of other predators, combining limb dexterity with jaw efficiency to subdue agile targets. Its long hind limbs, lightly muscled yet powerful, provided bursts of speed and rapid changes in direction, making sudden lunges highly effective. Tail flexibility added stability during agile maneuvers, ensuring balance while calculating each strike. The seamless coordination of limbs, tail, and sensory input exemplifies a predator whose mental and mechanical faculties operated as an integrated hunting system. Evidence from nesting sites and fossil assemblages hints at cooperative behavior, suggesting that Troodon may have hunted in loosely organized groups to improve capture success. Multiple individuals preserved in proximity imply either sequential use of hunting grounds or strategic collaboration. behaviors that could amplify the effectiveness of already intelligent predators. Such social tendencies, while subtle, demonstrate that predatory efficiency could be extended beyond individual ability, with group coordination enhancing survival and prey acquisition. These inferences suggest that intelligence in Mesozoic hunters could shape not only solitary tactics, but also collective strategies. Even subtle environmental cues, scent trails, shifting leaf litter, or minor rustlings triggered calculated responses, reflecting anticipatory decision-making rather than reflexive action. Troodon's brain allowed the integration of multiple sensory modalities to optimize hunting outcomes, from selecting the ideal moment to strike to evaluating when to pursue or disengage. Observing prey over time, it could exploit predictable behaviors, ambush, escape routes, or fatigue patterns, demonstrating tactical foresight uncommon among dinosaurs. Its ability to assess environmental and behavioral variables simultaneously reveals a predator capable of improvisation, adaptation, and learning, a stark contrast to the repetitive strike and reposition tactics of earlier Mesozoic killers. Fossil evidence, including wear patterns on teeth and claw marks on prey bones, supports the hypothesis that Troodon engaged in targeted hunting rather than opportunistic scavenging, reflecting a high level of behavioral complexity. Its teeth, though small compared to larger theropods, were densely packed and recurved, ideal for gripping and slicing smaller, agile prey. Repeated use did not compromise function, indicating a combination of durability and precision suited to a predator that relied on accuracy and strategic attacks. Each strike could immobilize, weaken, or kill efficiently, demonstrating that lethality could be engineered through intelligence and technique as much as size. Troodon's combination of speed, agility, and sensory sophistication allowed it to exploit ecological niches ignored by larger predators. It could traverse dense undergrowth, pursue nimble prey, and evade confrontations with more formidable hunters, while simultaneously coordinating attacks and exploiting environmental features to its advantage. By integrating mental acuity with anatomical adaptation, Troodon exemplifies a new dimension of predation, where thought is as lethal as muscle and coordination surpasses raw strength. Its success illustrates a profound evolutionary principle. The deadliest hunters are not always the largest, but those capable of anticipating, adapting, and executing with unerring precision. Observing Troodon, we see the culmination of millions of years of evolutionary refinement, where intelligence, dexterity, and sensory integration coalesce into a predator whose lethality is amplified by cognition rather than sheer size. Lessons inherited from giants like Acrocanthosaurus and Allosaurus on endurance, structural optimization, and environmental mastery are transformed here into strategic calculation, cooperative tactics, and precision attacks. In this predator, the balance of mind and body defines success, illustrating a principle that will echo in the apex killers yet to come. That superior cognition, applied with anatomical finesse, can produce a predator capable of dominating both intellect and muscle. As late Cretaceous forests grow denser and prey species more varied, these small but cunning hunters presage the emergence of predators that will combine tactical genius with formidable physicality, culminating the story of Predation's evolutionary arc. Last of the ancient murderers, Pectinodon beccarii. Tracing the faint shadows of Cretaceous floodplains, Pectinodon navigates its world with precision unmatched by earlier hunters. Its small frame belies the deadly efficiency embedded in every movement, honed by millions of years of evolutionary refinement. Where larger predators rely on force and intimidation, Pectinodon capitalizes on stealth, timing, and spatial awareness, slipping silently between vegetation and rocky outcrops, ever alert to the faintest tremor of prey or rival. Its environment is a patchwork of seasonal rivers, open glades, and dense undergrowth, each feature shaping the predator's approach and amplifying its tactical advantage. Skull morphology and delicate dentition reveal adaptations designed for pinpoint attacks rather than brute consumption. Serrated teeth, narrow and recurved, suggest a specialization in rapid strikes to vulnerable areas of small vertebrates, from juvenile dinosaurs to early mammals. Cranial reinforcements accommodate rapid snapping motions, minimizing energy loss while maximizing lethal efficiency. Fossil evidence indicates repeated use of these structures over the predator's lifetime, emphasizing that success depends on precise application of force rather than raw power. Sensory organs, from oversized optic lobes to acute auditory structures, create a predator whose awareness extends across multiple dimensions. Binocular vision allows depth perception necessary for high-speed strikes and accurate targeting, while heightened hearing and sensitivity to low-frequency vibrations detect subtle environmental changes, such as rustling prey beneath leaf litter. Neurological adaptations suggest rapid processing and integration of sensory input, allowing Pectinodon to make split-second decisions that could mean the difference between success and failure in a densely populated ecosystem. Forelimbs and claws function as instruments of tactical execution, each motion calculated to maximize efficiency and minimize energy expenditure. Flexible wrists and strong digits enable grasping and repeated slashing motions, complementing the precision of the jaws. Hind limbs, though lightly built, provide sudden bursts of acceleration and agile repositioning, allowing the predator to close the distance with minimal exposure. Its stiffened tail acts as a stabilizer, facilitating sudden pivots and countermaneuvers that maintain balance during high-speed engagements, a synergy of anatomy and strategy that ensures every strike lands where intended. Evidence of nesting and territorial patterns suggests not only individual cunning, but strategic understanding of the environment. Fossilized nesting sites, with carefully arranged eggs and protective placement in sheltered areas, indicate that Pectinodon balance predation with reproductive strategy, optimizing both survival and continuity of the lineage. Territorial spacing, inferred from bone bed distributions, implies knowledge of local resources and prey populations, hinting at an early form of environmental intelligence that transcends instinctual behavior. This dual mastery of hunting and habitat selection underscores the predator's holistic adaptation to late Cretaceous landscapes. Microscopic analysis of teeth and wear patterns reflects repeated, controlled predation, emphasizing precision over force. Marks on prey fossils show clean, directed cuts, often along vertebral and limb joints, revealing an understanding of anatomy and the most efficient means to immobilize and kill. Such specialization suggests that Pectinodon's success was not accidental, but the result of inherited behavioral strategies fine-tuned over generations, a living example of evolution's capacity to combine cognition with mechanical optimization. In the wider ecosystem, Pectinodon occupies a niche where intelligence, speed, and coordination outweigh sheer size, illustrating the apex of evolutionary refinement. Unlike contemporaneous small theropods, it thrived in both open floodplains and shaded underbrush, exploiting prey that was inaccessible to larger, less nimble hunters. Its role as a precision predator demonstrates that apex status need not correlate with physical dominance, but can emerge from a combination of sensory acuity, behavioral flexibility, and anatomical specialization. In doing so, it carved a place at the top of its ecological hierarchy, showing that evolutionary success is measured as much in subtlety and strategy as in brute force. Comparisons with earlier troodontids highlight the culmination of a long evolutionary arc. Where Troodon relied on social hunting and opportunistic tactics, Pectinodon integrates these lessons with enhanced anatomical refinement, combining rapid decision-making with superior mechanical execution. Its forebrain enlargement and sensory acuity surpass nearly all predecessors, reflecting a lineage that gradually shifted the paradigm of predation from reliance on size to reliance on intellect. In this way, the predator represents both a final refinement and a living record of the 300 million year journey of terrestrial hunters, from the first cautious tetrapods to sophisticated, strategic killers. Metabolic and physiological traits further define Pectinodon's predatory edge. Lightweight bones, coupled with efficient respiratory structures, allowed sustained bursts of activity and rapid recovery between attacks. This aerobic capacity, combined with low overall mass, enhanced stamina and maneuverability, permitting the predator to pursue prey over longer distances without fatigue. These physiological optimizations complement cognitive and anatomical traits, creating a predator capable of repeated, highly efficient engagements in diverse terrain. Its presence marks the culmination of a lineage that began with the earliest tetrapods experimenting with terrestrial hunting, now perfected in miniature yet deadly form. Pectinodon demonstrates that evolution, through countless iterations of trial and error, can produce hunters whose lethality is defined not by size or raw power, but by integrated systems of intelligence, agility, and precision. The lessons encoded in its anatomy and behavior reflect a grand narrative, the relentless refinement of terrestrial predation, where sensory perception, neural processing, and muscular coordination converge to produce one of the deadliest predators of the Cretaceous forests. Observing Pectinodon, we witness the final echo of millions of years of evolutionary experimentation, a predator whose form and function embody the culmination of the terrestrial predatory lineage, foreshadowing the complexities and specializations that would persist until the end of the Mesozoic. Beneath the sun-scorched plains and shadowed forests of prehistory, we have glimpsed the first architects of death, creatures whose instincts, cunning, and sheer persistence reshaped the world around them. Their silent strategies, from the tiniest ambush to the calculated strike, remind us that survival demanded both innovation and ruthlessness. In watching these earliest killers, we confront the raw elegance of evolution's designs, where life and death are inseparable partners. As their legacy echoes through time, the land itself seems to pulse with the memory of those who first mastered the art of murder. If you enjoyed this journey through prehistory, don't forget to like, subscribe, and leave a comment.